All right, and I will go ahead and record. All right, so today we're going to start talking about complex numbers. Like I said, I am going to talk a little bit about the homework, the Matlab related stuff on the homework here at the beginning, but I kind of roll through kind of a schedule moving forward. I told you guys last week that this week I would let you know what my anticipated schedule is, and in particular, when the first exam is going to be. So the first exam I'm targeting, I put that in bold and italics here. Exam 1 will be 7 p.m. on the 7th. That's a Monday. The reason I told you guys 7 p.m. is outside of class time. I will give you 3 hours for that, even though it is designed to be done in class. Okay. Talk about that more as it comes closer. I was originally hoping to do it the week before that, but with the fact that you guys are not supposed to have assignments due today through Friday and that kind of stuff, and the fact that we missed the class this week for the holiday, I have this is my plan. So you see, homework 2 will be due on Sunday. Homework 3 will still be due on Friday next week. Homework 4 will be due the Friday after that. And then we have our exam 1 that'll be coming up. We'll talk, you guys will have lots of questions about the format of the exam and all that kind of stuff. We'll talk about that as it gets closer. Okay. All right. So we're going to be jumping into into complex numbers. And you guys should have seen complex numbers, although probably saw them in high school. All right. Complex numbers are particularly important for a lot of the stuff that we do in ECE related stuff. We're going to be going past just regular complex numbers and be jumping into something called phasors and relating that to sine waves here in the near future, right? That's what we're going to be talking about next week. Okay. So before I jump into this, so our next set of classes are really going to be focused on material that is in chapter 4 of the textbook, okay, which talk about things related to complex numbers and how we deal with complex numbers. The relevant sections are these. Now, I have one complex number problem on homework 2, and it is very simple, okay? It should be completely covered by what we discuss here today, all right? So again, what I uploaded for you guys who don't have the book is chapter 3. That should be sufficient for what you need. Okay. All right. So let me go full screen here. All right. So some of you guys have hopefully most of you by now have looked at problem number 1 in the homework, right? And one of the things that it gets into is it looks at a problem like this one. I'm going to come back to my previous slide, but looks at a problem like this one, where I'm trying to take 2 functions and multiply them. And I'm trying to do that over a particular time frame. And my homework problem basically has 3 pieces. It basically says, I want you to do this problem 3 different ways. Part A says, I want you to use a for loop. Part B says a while loop. And part C says using this idea of what we call element-wise operations. Okay. First of all, if I'm talking about loops, what does that mean? I mean, and you guys know enough about C. Maybe you're still getting used to MATLAB, but if I'm talking about a for loop or a while loop, why do we do those things? Why do we do loops? What's the purpose of a loop?
To iterate through a function multiple times.
Yeah, I got to iterate through some function multiple times, and that means I better be running it multiple times, which means that if I need to loop, I need some kind of a stopping condition. I need something to tell that loop to stop. I've already gotten a couple of comments from people who said, my code never stops. Well, you didn't give it a stopping condition, okay? So in chapter 3, they talk about this form, and this is pretty similar to what you would have in C, right? It says for, and then this is the piece right here, right? Where it basically says, all right, for a particular variable name equal to some start value up to some last value, do the following operation, okay? Just like you would do in C, okay? Not really any different, just the syntax of it's a little bit different, but it's doing exactly the same thing you would do in C. All right, so what I want to do is I want to try to think about how we would use that format here. So MATLAB is matrix or vector based, meaning that if I want to take this cosine 3t and cosine 4t, I have to define those things at these times. Okay. So let's think about how I would do this. What I want to do is I want to compute cosine 3t times cosine 4t at those times. All right. So think about that. How should I set up the code to do that? If I want to compute these things at these times, what do I need to do? What would be the steps that I would need to follow? What's step one?
Declare a variable that has cosine 3t and another variable declare with cosine 4t.
Well, that would be my second step. What would be my very first step?
Define the t.
Yep, define t. So I'd have to say t equals, just like I have here, something that goes from -4 in steps of 0.01 up to 4. Okay. Now, I said this the other day, in Matlab, I don't have to put the semicolon, but I should. Okay. What does not having the semicolon do?
It outputs the value.
It outputs the value to the screen. I don't know how many points are in this, but I don't know if I did the number, it's probably like 8,000 points or something, right? It's going to write all 8,000 of those to the screen. That takes a while, right? You don't want that, okay? So use the semicolon, all right? If you want to see it on the screen, then you do this. You don't put it there, but oftentimes you don't want to, okay? So, and then I'm not sure who said that, but the next step is to define these two things. So I'm going to say, let's make a vector G that's equal to cosine of 3 times, right, the asterisk t, okay, semicolon. And then I make another one H. And I'm just making up those variable names, okay, like that, 3 times t and 4 times t.
Does the cosine for j and h should to be in a bracket as a vector or as a matrix?
So I just define it like it's a variable, right? So I can say g equals this, h equals this. I don't need to do anything else, right? It's gonna come out, and that's a great question. If I do it like this, g equals cosine, then g is going to have the exact same size as t, and h is going to have the same size as t. So if, let's take a look here real quick. So I've got this same code here in Matlab. Okay. So what I have in my Matlab code is, so I defined my t vector, I defined g, I defined h. So I'm going to take those things, I'm going to evaluate those in Matlab, and then let's look at it. All right. So if I want to know, what was the command I said? If I want to know how big those are, the size of them, the dimensions of them, what's the command I use?
Length?
Isn't it just size?
Yeah. So I heard a couple of good thoughts there. I'm going to do size first, size of t. All right. So what does this say? The fact that size came back and said 1 and 8,001, what does that mean?
It's a row vector with 8,001 entries.
Yes, there's one row and 8,001 entries. Okay. So G is going to have the exact same size because I said it's defined at all the points that exist in T, right? And then H would be the same thing. Okay. H would be the same thing like that. So looking at that, what if I write code like I did there, right? G equals this, it's going to define G at all those points in T, and it's going to define H at all those points in T. Okay. What would be my next step? If I wanted to create cosine 3t times cosine 4t, what would be my next step?
Declare another variable just to multiply both G and H.
So okay. So if I multiply G and H, so G is a variable now that has a size, it has one row and 8,001 columns. And the same is true for H. Okay. If in matrix terms, if I do G times H, okay, a lot of you guys have taken linear algebra, G times H, if I multiply two vectors that are one row like that, what's going to happen when I do that matrix multiplication?
It's undefined.
It's undefined. Okay. So MATLAB treats these things like they're vectors. It's matrix based. It's going to say, you know, that's you're trying to do a matrix manipulation that's not possible. But that wasn't what you were trying to do. Think about what it is that we're trying to compute. If I'm trying to compute cosine 3t times cosine 4t, then what I'm trying to do is I'm trying to make an output vector that's going to be g at well, let me do it this way. I'm trying to compute an output that looks like this. Cosine of 4 times -4 at times cosine of 3. It's out of the way. 3 times -4, right? That's the first entry. Then I'm trying to do something. The next one would be cosine of 4 times, I don't know, -3.99 times cosine of 3 times -3.99, like that. Okay. So I'm trying to create an output vector that's defined at all of those values in this time vector, right? And I'm needing to multiply each entry in G by each entry in H. You guys follow that?
Would you have to do the inverse of 1?
Well, so one way to do it is to do loops, right? I could basically go through each element in G and each element in H and do the multiplication like that. Okay. So how would I set that up? How would I use a loop to do that? All right, let's look at the way the for loop was set up, right? So I'm going to need a for loop to do it. So let's just say I've got for and end. Looking at the syntax of the for loop in MATLAB, for and end, right? So what I need to have is I need to loop through from some starting value to some ending value. Now there is an exact example for this. There's a MATLAB example. It's script 3.16. And I don't know off the top of my head what page that is, but let me say it's about 147. Looks exactly like this. Okay. Looks exactly like this. Okay. How should I set this up in this case? Given the way I set these up, so I've got G and H. And let's say I want X to be cosine of 3t times cosine of 4t. How would I set up a loop so that I made this multiplication of each individual element?
This is going to be start from -4 to the length of t.
Exactly. So you want to start at a time t equal to -4, and you want to end it at time t equal to 4. The tricky thing is, I need to know. I need to basically loop through every element in this vector. So I want to do something at -4, and then at -3.99, and then at -3.998, and then so on and so forth. Easiest way to do that is to do it by index, right? So I would index through that time vector. So to do that, what I do is I say, all right, so I want to do a calculation that says I want to compute, my output's going to be called X. I'm going to say I want X sub I to be equal to G sub I times H of I. Like that. And I'm going to put a semicolon after it. So in other words, I want the ith entry in G times the ith entry in H to give me the ith entry in X. You guys follow that?
I'm sorry, I get confused here for a second about the G and H.
Yep.
G is supposed to be a variable, not a function. I'm sorry, just like.
So G is a variable. That's right. And so when I say G of H like this, I'm saying pull out the entry at location number I.
Oh, okay.
Okay. So what I have to do is I have to define I as a variable, right? And so the way I do this is I'd say, well, if I want the first entry, I would say X of 1 is equal to G of 1 times H of 1, right? That would give me the first entry. That takes the value at -4 in G and the value at H at -4 and multiplies those together to give me the value of the output at -4, right? But -4 is the first entry in that vector. Okay. You guys follow that? So I need to define, if I look at my for loop definitions here, right? So variable name, I'm looping through a variable here. So variable name equal to a start value to an end value. So what I want to do then, what variable, if I'm looking at this thing, this for loop that I've written out here, what variable would I be looping through?
I.
Yeah, I is my index. So I would say for I equal to, I'm going to say from 1, because we said in Matlab, all of our vectors start with entry number 1, not like C where they start at 0. In Matlab, they start at entry number 1. So starting at 1, and then it says my increment value to my last value. So I'm going to say my increment value is going to be what? What do I want I to go up by every time?
0.00.
Well, I want the time vector to go up by 0.001. That's right. But if my time vector is going up by, I want my I vector to go up by 1, right? Because the next index corresponds to an increase in time by 0.001, right? So this would be 1. You guys follow that? My increment value in the time vector is 0.002. But what that means, or 0.001, but that means if I looked at the time vector, right? If I looked at t, it would be -4, -3.999, -3.998, like that, so on and so forth, where this would correspond to I equal to 1, 2, 3, like that. You guys follow
In MATLAB,
that?
can't you just get rid of the incrementation by 1? And if you don't specify, it always increments by 1?
Let's not make this any more complicated than we need to, but that is correct. Yeah. I don't want to confuse anybody. Put the increment in there. If you don't put it in there, it becomes implied that it's 1. But I always put it in there. All right. If I use the general form of this, right? From a start value with an increment to a last value, like that. Now, how do I know how far to go? How do I know where to stop?
Stop at the length of t, right?
Stop at the end of the vector, right? At the end of the vector. So he said the length of t, and that is correct, right? So what I want to do is I want to figure out how long this vector is. Okay. Well, how do I figure out how long the t vector is or how long the g vector is, right? Well, so one command that I ran right there at the screen, I ran this command called size. Okay. What did size output? What does this look like here? Is this an individual number?
No, it's an array.
It's an array. Okay. So one thing I could do is I could say, well, you know what? If I can get a single number here, is if I say I want to look at the first row, second entry of that answer. So let me do this. I could do this and define a variable y, right? And I could say, well, that number 8001 would work for me. So I could say, I want the first row, second entry of y. That works, right? That gave me a number that tells me how long that time vector is. That's one way to do it. There is a command called length as well, right? So if I do the length of y, all right, oh, not the length of y, the length of t. Sorry, length of t. I see that the length of it is 8001. Length is another command that will tell you how long a particular array is. I talked about size on the first day, but length is another one that tells me if I just have an individual row or an individual column, it tells me how long that is. All right, so let's look at my final code here. All right, so the code I wrote, notice what I did was I said n is equal to the length of t. So I figured out how long it is. And then I wrote my for loop to say, let's go from I equal 1 in increments of 1 up to this variable n. And then let's compute x sub I equals g sub I times h sub I, like that. And that will create for me a vector that has the same length as g and the same length as h and the same length as t that contains at every entry the multiplication of each of the entries in the two g and h vectors. Okay. That's the basic way of how we set this up. Now, there is an exact example like this. What did I say it was? I think it's script 3.16 on page 147 of the book. All right, that looks just like that. All right, that you can try to follow. All right. Questions about that?
I'm getting a little bit confused about the syntax of G of I. I'm like the programming coming inside my mind with the syntax, but G you told us as a variable, but you type it in the for loop as syntax of function, if I'm not mistaken. This means
well, so I think what you're thinking of is if you were working in C and you wanted to pull an index at location 1, you would have square brackets like that, right? That's where yeah. MATLAB doesn't work like that. In MATLAB, it's parentheses. That's going to give me the first entry. If I have a variable named G, then it's going to give me the first entry of that. If there was a function called G, right, then this would be an argument passed to that. But because I have a variable named G, it's calling that the entry at that point. That's a great question.
So if I typed it in a way that's x of I equal cosine 3i multiplied for cosine 4i, if this is going to be works too?
You've got to be careful like that. It's a great question. He's asking a good question. So the other way I could do this is, let's say I wanted to make another variable. I'll do it this way, y of I. I could say this is cosine of 3, not 3 times I, but it would be 3 times t of I. Times,
okay.
Right? So it'd be 4 times t of I, like that. Follow?
Yes, sir.
Yeah, because I want the number value that exists at that index.
Yes, I got it now.
Okay.
Thanks, sir.
Yeah, that's a great question because, yeah, I guess in C, right, you'd have square brackets typically when you're dealing with an array variable like that. But in MATLAB, it's all done with the parentheses. And that's in part because I think the square bracket is reserved for defining vectors and matrices like this. Okay. All right. Now, if I asked you, okay, well, so the code that we just developed is how I would do this with a for loop. I could use a while loop to fill out every element in this X vector as well, right? So if I look at if I look at a while loop, right? While it's set up in MATLAB the same way, while and end, right? And then I put whatever operations I want to be repeated. With a while loop, what's the difference? I mean, you know enough from C. What's the difference in a for loop and a while loop? What's the for loop doing that the while loop isn't?
A while loop, you have to make your own like stopping condition. You don't have the like incrementing.
Yes. And you have to change whatever variable you're looping with, you have to increment yourself, right? So this while,
don't you have to use logical operators for while loops?
Yeah, and you'll have to use a lot. So while a certain condition is true, right? So in this case, you can probably imagine what the condition would be, right? So as long as I haven't reached the end of the time vector, do the computation G times H, right? Or let me say it this way: G of I, the ith entry in G times the ith entry in H, like that. Okay. That's how I would do it. And then I would have to increment I myself, and I would have to make sure that I hasn't gone too far. Okay. I don't want to say any more about that. I think you guys should be able to figure that out. But each time I go into this, it's wanting to figure out, has I gone too far? Okay. All right. It's very similar to what you would do in C. Some differences, right? So this parentheses instead of the square bracket, right? To get a particular element of an array. And the other thing it's different is the first entry is always number 1, the number 1 entry, not the number 0 entry, unlike it is in C. Okay. Now, everything I just talked about, it seems like doing this type of operation, it's a pretty common thing to want to do, and you wouldn't want to write a for loop every time you do it, right? So MATLAB has another operation, which is described there in the book, what we call element-wise operations. So if I want to compute, I want to multiply every entry in this vector by every entry in this vector, what I can do is I can do a dot multiply. And then what it does is it purposely multiplies the first entry in this guy times the first entry in this guy, and the second entry in this guy times the second entry in this guy. So the other way to do this is I could say, well, I want X to be equal to G dot multiply H. All right. This is a particularly useful way of looking at this, right? This is a useful function. It's useful functionality. One thing I recommend is, particularly when as you work through the homework, it's actually maybe a little bit more helpful sometimes just to use the straight MATLAB and not to put it straight away into the Canvas tool, because sometimes you can it's a little bit more flexible sometimes to see the outputs that come from regular MATLAB, because oftentimes if you're not thinking carefully about the size of these variables, you may get some really weird things that happen when you do the multiplications. Okay, you guys, it's hard to describe that until you start having those problems, but you can start running into some problems pretty quickly. And we'll talk about that a lot as we get into the first project, which will be after the first exam. Okay. All right. So that should clear up some confusion, I think, with respect to problem one. Again, there's examples that are almost exactly what I'm asking you to do in problem one in the book. So in particular, like I said, this particular script is very, very similar to what I'm talking about. Okay. Any last questions about that for now? All right, you guys are quiet. If there's a lot, I mean, again, my office hours are scheduled for this evening. If people want to go through some MATLAB examples, I'd be happy to do that there for sure. Okay. All right. So I want to jump into one of my main topics for today, which is complex numbers. Okay. And we got a couple of things that we need to cover about complex numbers to be able to wrap up the homework. So looking at this, the thing I have right here, this is something that looks to a lot of people like it's got every element of math that you've ever really done before, right? So I have this e to the I omega t. Somehow I've just related exponential numbers to complex numbers, or exponentials to cosine and sine. What is this I? Anybody know what the I is that I've written there?
Is that the square root of -1?
It is the square root of -1. Yes, that is correct. It is what we call the imaginary number. All right. Now we're going to talk a lot about that, but the imaginary number somehow allows us to relate exponentials to cosines, and that sounds like it is weird and probably not all that particularly useful, but it turns out to be incredibly useful. Particularly if we get into the subject of digital signal processing, which is a big part of what we do in computer engineering in particular. So give an example. So you guys have heard, a lot of you guys hopefully have probably heard the term of DSP, right? Digital signal processors. So these are a type of microprocessor, these DSPs. And what I have here is an example system. This is a noise cancellation. So if you had noise canceling headphones, okay, noise canceling headphones, what they do is they have some microphones that basically are listening to sort of what's happening in the environment and trying to make those things go away. All right. So the sound that goes to the speaker, all right, doesn't have this kind of background noise. But a key part of this thing is that I need to do some signal processing. I'm measuring something. I'm measuring a signal that comes from a microphone, and I'm trying to make that signal go away. So the example that I have here, right? This is what's measured, let's say, or this is what's coming out of the speaker, and this is in time. So I'm looking at a signal that's measured in time. And I'm trying to make that signal basically become a constant, trying to make that noise go away. Well, to do that, if I look down here at the bottom, right, what I have is sort of a set of frequencies. And I'm saying, how much energy do I have at each of those frequencies? And I'm realizing this is probably a concept I should probably give you guys. So let me see if I can real quick. Let's see how well this works. I'm going to try to show an app on my phone. Let me see. Okay. See if I get the right app here. Thought I had it. Okay, here it is. All right. So right now, if you guys look there, how well can you guys, maybe I need to look at myself here.
Just
All
bring
right.
it up a little.
Yeah. All right, there we go. So you guys, okay, so if you look at what I see, every time I'm talking, you see these sort of spikes appear on my phone. Okay. Can you guys read what's on the x-axis here? Those numbers?
Yeah.
Okay. So what those are frequencies. Okay. And what this is doing is it's doing a real-time analysis of what my voice looks like. So my voice is made up of sinusoids at different frequencies. And so are your voices, everybody's voices are. Okay. And so when I look at this, right, what it's doing is it's basically doing an analysis to say at what frequencies are there sine waves coming out of my voice. So it's analyzing the signal that's hitting the microphone, right, and telling me what frequencies where I have signals. That's incredibly useful for something like this noise cancellation that I've got up here on the screen. All right. Now, what I just showed you, you may have heard this term before. It's a fast frequency transform, an FFT. All right, you may have heard that before. All right. Basically, what it's doing is it's useful to look at a signal and say, what's in that signal, right? I need to do that, right? To do that analysis, I need complex numbers, imaginary numbers. Okay. They make the analysis a heck of a lot easier. So we're not going to get into the how we use it just yet. We're going to get into remembering what complex numbers are. Now, if you guys are taking 2112 this semester, they're very commonly used in 2112. Almost all of 2112 is about using complex numbers because they make the analysis of circuits a lot simpler. Okay. Now you may look at that, oh, it doesn't seem simple, right? Because they're imaginary numbers, but it actually does make the analysis a lot simpler. What it ultimately allows you to do in circuits is to not use differential equations. So you can get differential equations out of the picture and do all your analysis with complex numbers, which turns to be an algebra problem. All right. So that thing I just showed you on my phone, all right, what it's doing is it's basically taken a digital version of my voice, okay, and it's doing this thing called a fast Fourier transform, all right, which involves this I right here, this complex number, okay. That's what it's doing. This is a very common thing to do in real-time signal processing, which is what a lot of you guys will probably get into. So inside a digital signal processor, right, what you end up with is you're doing all sorts of operations inside the processor. All right. The key thing is if I take the variable, so it takes the samples of my voice, and often if it takes this FFT, it basically computes complex numbers. Complex numbers have a real part and an imaginary part. They have two numbers together. And we're going to talk more about that today, and I shouldn't write this J thing here yet. All right. This is a complex number, has a real part and an imaginary part. In a digital signal processor, you're able to do a process on this complex number. Okay. In terms of operations and things like that. So if I wanted to multiply two numbers, if I can store a number like this, as opposed to storing it as A and B separately, what does that mean from a computer engineering perspective? What does that mean in terms of computing? If I wanted to do, let's say this was this was one number, right? And then I'd add another complex number that was C plus JD, all right, ID, that way, right? If I wanted to multiply, if I wanted to do x1 times x2, right? If I wanted to multiply those two numbers, why would it be better to use this form than it would be to separate them out into individual variables? Anybody know?
The one variable takes up less memory space and can be accessed quicker.
That's a great way of thinking of it. So it takes up as much memory space. Okay, but that's a great way of thinking of it. What else would be a potential benefit?
Is there less room for error?
Not necessarily less room for error. Maybe.
I's could disappear because they're square root of -1. So if you're doing a multiplication, they could go away potentially.
No, not well. They could maybe in some ways. Basically, it's going to be fewer computations, right? If I wanted to multiply x1 times x2, maybe we'll come back to this point after I've talked a little bit more about complex numbers. But if I want to multiply x1 by x2, I can do that in one step if I have a processor that can handle complex variables. If I don't, then it becomes kind of a multi-step process, okay? And that becomes pretty complicated, right? So in other words, in a complex processor, it's able to do a lot of things in a single operation that otherwise would require lots of operations in what we would call a fixed point processor, right? And again, some of you guys may be like, what the heck is he talking about, right? Some of you probably have a little bit of context for this at least, but I wanted to give a little bit of grounding that this stuff does matter. So the complex numbers, imaginary numbers, are useful to us. And they're used by computer and electrical engineers for all sorts of different problems, and signal processing is one of them. So that frequency analysis I showed of my voice, complex numbers are right at the heart of that. All right, to do that, I really need to have an understanding of complex numbers. So we got to go back to the basics. All right, complex numbers. So you guys know the imaginary number, somebody's already said it, I is equal to the square root of -1. All right, they are a weird concept to a lot of people. And I guess I wanted to say with this is complex numbers are weird, but a lot of numbers are weird. All right. Why were numbers invented? Anybody really know the answer to that? Why were numbers invented? If you were a caveman, why would you have invented numbers?
Would it be for trade?
For counting. Yeah. I mean, so in trade or whatever, I would need to count stuff. Okay. So let's say you took, so the example here is, let's say I'm counting apples, right? So I have 2 apples, and then, I try to take away 3 apples. That leaves me with -1 apples. Okay. The guy who invented numbers could not wrap his head around that, right? What is the meaning of having -1? It means that I have a negative amount of something that I'm trying to count. In other words, it doesn't make a whole lot of physical sense. So if your context is that, you think of numbers as something for counting, having -1, -2 doesn't really mean a whole lot, right? And in fact, over time, right, if you look at all the different number systems that have been developed, right? So this sort of quick example, right? Back to Egypt, ancient China, ancient Rome, or whatever. If you look at them, look at the Romans, for instance, they didn't even have 0 as a number, right? Because 0 didn't mean anything, right? Because I'm counting stuff. It doesn't mean anything to have 0 of something, right? It only means something to have something other than 0. So there's a lot of disagreement for a long time. It wasn't until we got to relatively modern times that we said, you know what? We need to have a lot more numbers to be able to capture all the different things that can happen in the world. Okay. So the idea of having a number that is imaginary always sounds kind of silly to a lot of people. But, at one point in time, -1 and 0 even seemed pretty silly to most people, right? Because they didn't seem particularly useful for anything. But we already know that those are useful numbers, right? If I say a current in a circuit is -1 amps, that just means that I have 1 amp, but it's going in the opposite direction that I drew my arrow, okay? So there's physical meanings to these things that are useful. Now, where did complex numbers come from? When you learned them before, in what context did you learn them?
When doing square root of a number?
Yeah. So let's say, so you learned, here's a real flashback. What is the fundamental theorem of algebra? Anybody know what that is? Anybody remember that? It's fundamental. So hopefully somebody knows it.
The order of an algebraic equation is equal to the number of solutions.
There you go. All right. Yeah. So in other words, if I looked at, x squared equals 2, right? Or let me take a simpler, x squared equals 4, right? How many solutions are there to that? What values could x take?
Plus and minus 2.
Yep, plus and minus 2. The equation is second order, so there has to be 2 roots. Okay. So how about, so in other words, 2 roots. So in other words, x squared minus 4 equal to 0 has 2 solutions. Okay. That means that x squared plus 1 better have 2 solutions. And there we have it. That's what x squared plus 1 looks like. Does that have 2 places where it crosses 0? Doesn't look like it. No. I mean, so it's not a trick question. It doesn't look like it, right? However, if I begin to look at numbers, and there's a whole theory of what we call complex analysis that looks at this in kind of a multidimensional space, where you can say that actually, if I look at this in a multidimensional space, there are some places where it crosses the 0 plane. All right, we don't need to get into that, but if I looked at this expression, you'd say x squared equals minus 1. So x has to be equal to what?
Plus and minus the square root of -1.
Yeah, plus or minus the square root of -1. But that number, the square root of -1 is not defined. We define that as the imaginary number. Okay, so we say this is plus or minus I. All right. If I go into Matlab, Matlab has that number, and it may not because I was using it as an index. Let me see. So if I clear all, I'm going to clear out all my variables. If I write I, let's notice what it says. I is equal to 0 plus 1 times I. Matlab recognizes I as the imaginary number. Okay. So in general, we talk about complex numbers. All right. And so I want to talk about the form of a complex number, right? Because I've used that term a little bit here as we've gone through it. I am not going to use I, and electrical computer engineers don't use I very much. We call it J, all right, the imaginary number, I guess, if you will, right? We call it J. Why don't we call it I? Anybody know?
We already use I for current.
We use I for current, and as you guys will see in 2112, it'll get pretty confusing if you do it that way. All right, so we use J, and Matlab recognizes J as well. So if I go in here and I type J, J comes up as 0 plus 1I. All right, so both J and I are recognized as that. Now I know what's going to happen is some of you guys are going to say I equals 2. Okay, then if I type I, notice that I is no longer the imaginary number. That's why I said before you run your code, you always want to clear out your variables, all right, to make sure that it goes back to what you originally thought it was going to be. I tell you right now, some of you guys are going to run into problems as you go through the homework because you forget about this fact, okay? You may have, you are free to call I, whatever you want. Matlab defaults to thinking of it as the imaginary number, okay? All right. I've used this term complex number. A complex number is a number that has multiple pieces to it, a real part and an imaginary part. And where would a complex number come from? Well, maybe if I had something like, to my previous problem, let's say I had, x squared equals, -2. So in this case, I wouldn't get a real part, but there would be equations that could potentially give you real and imaginary parts. Okay, so a complex number has a real part and an imaginary part, and we draw it in a complex plane. All right, so what we say is, and I guess just to be consistent here, this should be Z's, Z, and Z. So I draw a complex plane, right? So the x-axis here is where I draw the real part, and the y-axis is where I draw the imaginary part. So I said if my general form of a complex number z is equal to a plus jb, okay, what I'm saying is the x-axis value is my real part. So the x-axis value is my real part. The y-axis value is my imaginary part. And I can draw it in this complex plane in different ways, okay? So the length here, right, is this length is the imaginary part. This length here is the real part. Now notice I did a couple of things. I defined a couple of things here. So I said A is the real part of Z. Okay, I'll write it this way, real of Z. And B is the imaginary part of Z, right? So I define them, I define the real and imaginary part. The way I think about this, the way you think about it, looking at this in a complex plane, I call it, is it's just like thinking about vectors in physics, right? So in physics, remember, you'd say, well, what happens if I have a, 3x hat plus 4y hat? Well, in physics, what would that look like? How would you draw that vector, 3x hat plus 4y hat?
Just a normal vector going up to the right.
Yeah, so yeah, it would have a x length of 3 and a y length of 4, right? It would be in the first quadrant. Basically, if I told you I had a complex number that was 3 plus 4j, that guy would look the same. Okay, he would go up 4 and he would go to the right by 3. All right, and its real part is 3 and its imaginary part is 4. Okay, so the other thing that we do, there's multiple different forms of complex numbers. Okay, we can also write these in what we call polar form. All right, and when we write in polar form, what we do is, in polar form, we express this thing as not just a real and imaginary part, but as a magnitude and an angle, okay? So the height of this, so this guy goes up B and goes over A, right? So A was the imaginary part. So remember, A is the real part. A is the real part of Z, and B is the imaginary part of Z. Like that, okay? So how would we define here the magnitude of that vector in terms of B and H? So just think about this thing here like it's a triangle, right? If I think of this like it's a triangle, how can I define the magnitude of Z?
Did you do the square root of a squared plus b squared?
You got it. Pythagorean theorem, right? Square root of a squared plus b squared is my magnitude, okay? How could I define the angle that I've written out here, phi? How could I define that?
Arctan.
Yep. Arctan of what?
B over A?
Opposite over adjacent.
Yep. Opposite over adjacent. So B over A. In other words, the imaginary part over the real part. Okay. So I can define these numbers in a couple of different ways. Now there's problems with the arctangent. Arctangent is defined between what angles? Anybody remember?
All positive, I think. 0 to pi.
It's well, so in radians, it's negative pi over 2 to pi over 2. So what are those angles in degrees?
Negative 180 to 180.
Nope. Negative 90 to 90. So pi over 2 is 180, right? So pi over 2 is 90 degrees. Negative pi over 2 is negative 90 degrees. So if this is my first quadrant, right? This is my second quadrant. This is my third quadrant. This is my fourth quadrant. What happens if my vector is over here? So first of all, let's just go through, let's go through just to remember, make sure everybody remembers angles, right? So if I'm talking about a vector that is over here, pointing in this direction, right? What's the angle of a vector that is pointing in this direction?
0.
0. What's the angle of a vector that's pointing straight up?
90.
90, right? If I'm pointing over here, what's my angle?
135.
135. Over here would be 180. Over here would be what? 225. Over here would be 270. And what's this guy? This would be
315.
315. Yeah, there we go. Right? So if I'm pointing over here, that's an angle that's not defined by arctangent. Okay, we'll look at an example here in a second. All right, let's do some examples here. All right, so 3 plus j4. All right, 3 plus j4. How would I draw that in my complex plane here?
3 to the right on the x-axis.
Yeah, 3 to the right, and then
4 up.
4 up, right? So I'd go over 3 and then up 4. So my vector would be here. Okay. All right. So this would be z right here. This would be my vector z. Okay. So its real part, this would be 3. Its imaginary part would be 4, like that. All right. So let's say I want to put that into polar form. So in other words, I want to know what is the magnitude of z and what is the angle of z. So sometimes I write that as angle z, like that. So I want to know its magnitude and its angle. So what is its magnitude? How do I get that?
Pythagorean theorem.
Pythagorean theorem. Nice and simple. Magnitude of z is equal to 3 squared plus 4 squared. Okay. And that works out to be what? I think it works out to be 5, doesn't it?
5.
Yeah.
I'm so sorry. This is supposed to be 4j squared or just only 4 squared?
No, that's a great question, right? This is just like if I said to you yeah, great question. 3x hat plus 4y hat. If you had that in physics, right? And I said to you, what's the length of that vector? What would you tell me?
3 squared plus 4 squared.
Square root, right?
Square root, yeah.
Yep. 3 squared plus 4 squared. The imaginary, that's a great question. The imaginary part, can we go back? The imaginary part is the coefficient on the j. Not the j is not part of the imaginary part, right? So this is just like in physics where you had these sort of unit vectors, except there is no unit vector on the real part, okay? So the j is not part of the imaginary part. So it's just the two coefficients, 3 and 4. So 3 squared plus 4 squared. It's just, think of it just like it's a vector, right? And forget that the j is even really there. Just think of it as a vector.
Gotcha. Thanks, sir.
Yeah, great question. So all right, so that's how I get the magnitude of it. How do I get the angle of it?
Inverse tangent.
Inverse tangent. Okay, so and it becomes the angle of z is equal to inverse tangent or arctangent of the imaginary part over the real part. And that works out to be, I think, about 53 degrees.
Mm-hmm.
Now, notice what I did here is I did this in Matlab. Matlab has a function atan, which is arctangent. All right. And one of the things that, so I mentioned this here, let me jump and come back, but Matlab has a lot of useful functions. All right. These are the key ones here: real, imag, abs, angle, and phase. All right. One key thing about all of the trig functions in Matlab is they all are in radians. So if I say to Matlab a tan of 4 over 3, it's going to give me an angle in radians. Always. So what I do is I say I have to convert that angle to degrees. So I multiplied by 180 over pi. What is 180 over pi? If I have an angle that has units of radians, right? So if I have an angle, let's say phi, right? And this guy has units of radians. If I want to convert it to degrees, what do I have to multiply by?
1 over radian?
Yeah, so 180 degrees corresponds to pi radians. And that's basically just a standard unit conversion, right? So that's what I always do. So if you look at this piece of code I wrote here, I said a tan 4/3 times 180 over pi. Now MATLAB has some other functions that you guys will find useful. Radians to degrees and degrees to radians. All right. So in other words, radians, and you can just type in help rad to degrees and help degree to rad, and you'll see more about those, right? So let's just try this real quick. All right. So if I type in here at the command window, a tan 4/3, I don't get 53 degrees. I get 0.9273 because its default was radians. So if I multiply by 180 over pi, I get the 53 degrees. So I did my own manual conversion. But there is this function rad to deg, rad to degrees. And I can put that a tan in there. And that'll do the same thing. All right. I don't, you know, you're welcome to use those functions. I find it simple enough to just know how to do the unit conversion, right? I multiply by 180 over pi, and that makes the conversions for me. But MATLAB has these other functions for me: real, imag, abs, angle, and phase. So let's say I defined for myself here. Let me go to here. Oops, not here. My command window. And let's say I said z equals 3 plus j times 4, like that. Okay. If I said real of z, it's going to tell me that it's 3. If I said imag of z, what's it going to tell me if I say what's the imaginary part of z?
4.
Just 4, not 4 times j, right? It's going to be 4. Okay. Just that coefficient. If I type abs, what do you think that's going to give me? Anybody know?
The magnitude?
It's going to give me the magnitude, the absolute value of it. It's 5. That's the same thing as if I did square root of 3 squared plus 4 squared. All right. Now that I define or mention two other things here, angle and phase. Angle will give me values between in radians 0 to 2 pi. Phase will give me values between negative pi to pi. Both of those cover 360 degrees, but they do it differently. I will almost always in the homework ask you to give me results in degrees. And I will almost, in fact, I don't know that I ever ask you to do it in radians. I think I always ask you to do it in degrees. And I almost always ask you to do it between negative 180 and 180. There's a couple of reasons for that. I don't know any real engineers in the real world that really ever talk in terms of radians. Okay, if you go to Duke and you say, well, you know, I have a 2 pi over, my phase B is at 2 pi over 3, they'll look at you funny, right? You say that I give angles in degrees. All right, so, and I often, sort of the industry standard usually is to give those angles between negative 180 and 180. We could talk about why that is, but for now, I just suffice it to say, if you look at your homework, I will almost always tell you to put things between negative 180 and 180. So if your answer is correct, but out of that range, you may see that it's coming up wrong, but it will almost always say in the question, make sure you put your angles that way. Okay. What happens if I said I had something like this? Negative 3 plus j4. Okay. How would I draw that guy?
That's going to be in the second quadrant.
I mean, the second quadrant, right? So this guy is going to go over 3 and up 4, like that. All right. Now, if I said, what's the magnitude of that? What would the magnitude of z be?
Still be 5.
Still be 5, right? So it'd be, in this case, negative 3 squared plus 4 squared, like that. What the angle of z? How would I get that?
I have a question. This is going to be the same if it's going to be plus 3, positive 3 minus 4j. Does the minus here is going to be injected to 4?
Not sure I followed what you asked there.
So like, for example, if z equals 3 minus 4j, so for the square root is going to be 3 squared plus minus 4 squared.
Yeah, the magnitude is going to be the same no matter what, right? It doesn't really matter if those real and imaginary parts are negative or positive because you're talking about lengths. If I'm talking about the angle here, how would I get the angle of this thing?
Would you add 90 degrees
All
to
right,
whatever
so,
the tangent was?
well, so let's see. So tangent of, how do I do this? I would say the imaginary part over the real part, like that. Now, what did we say? What angles did we say tangent was defined between?
Pi over 2 and negative pi over 2?
Yeah, so 90 degrees and negative 90 degrees. What angle am I at here? What angle is this pointing at?
Around like 135.
Yeah, definitely outside of that 90 to negative 90, right? 90 to negative 90 is somewhere in this range, isn't it? It's in the first or second quadrant. First or fourth quadrant. What quadrant am I in here?
The second.
The second, right? It's not defined there. So if you go back to what you learned in school, back in high school, if you get a vector that has an angle over that direction, I need to add 180 degrees to it. And that solves that problem. Okay. So if I said something like this, right? So a-tan of 3 divided by negative 4. Okay. And let's say again, I want that to be in degrees. So I'm going to do 180 over pi, and I'm going to add 180 degrees to it. Now it tells me that's at 143 degrees. That looks about right to me. All right. I mean, again, 143 degrees makes sense because I know this point right here would be 90 degrees. And this point right here would be 180 degrees. Okay. So if I'm over in the third or fourth quadrant, I add 180 degrees. Okay. And I'll upload sort of a cheat sheet on complex number stuff. But if I'm ever in the second or third quadrant, I have to add 180 degrees to what tangent does for me. Now, the other thing I can do in MATLAB is I can use those phase and angle commands. So if I say phase of z, MATLAB takes that into account for me. All right. Or if I use the command angle, MATLAB takes that into account for me. Okay. So I kind of skip that step. All right. Now, one thing we have to do a lot of is add and subtract and multiply and stuff with these complex numbers. Okay. So the way I look at this is, let's say I've got two complex numbers here, 4 plus, so I did this, all right, in terms of I here, 4 plus I and 1 plus 3I. If I want to add those together, I just add the real parts and add the imaginary parts, right? So 4 plus I, and I want to add that to 1 plus 3I. Well, that just becomes 5 plus 4I, right? So I do 4 plus 1 is 5, 1 plus 3 is 4. So in other words, I can do these calculations very easily in rectangular form, okay? But if I'm going to do multiplication and division, it's a lot easier to do it in polar form, okay? So let's say I had, and I wanted to talk about this Euler identity. I'm not going to talk about that here today. All right. Let me do this. We'll talk about this next time. You don't need it for the homework. All right. Let's say I want to multiply. Multiply or divide. Okay. And let's say I've got two complex numbers. Let's say I have Z1 equals 3 angle 45 degrees. And let's say Z2 equals 2 angle, I don't know, 30 degrees. Okay. If I said, where are those two vectors? Let's draw them. Where would 3 angle 45 degrees be? Where would I draw that?
Both of them in the first quadrant?
In the first quadrant, it would have a length of 3. And this angle here would be 45 degrees. Where would so this would be Z1. Where would Z2 be?
Underneath you, underneath Z1.
Yep. So Z2 would be somewhere over here. He's a little bit shorter in his length, and this angle would be 30 degrees. Okay. Now, if I wanted to multiply and divide those vectors, what I do is if I say what's Z2 divided by Z1, okay, how do I do that? Anybody know? How do I do that division? What's the easiest way to do that?
Do you have to split them up into their components?
Well, I could. So if I split them up into your components, I mean, in other words, figure out what's the real part, what's the imaginary part. Is that what you're suggesting?
In a sense, and then treat each part individually?
Yeah, you could do that. The other way to approach this is, and you may have seen this when you manipulated vectors in high school or previous, is I can divide the two magnitudes, and the angle becomes the angle of Z2 minus the angle of Z1. So I divide their magnitudes and subtract their angles. So in this case, I'd have the magnitude of Z2 divided by Z1 is 3/2, right? Or 1.5. Oh, sorry, Z2 over Z1, sorry, the wrong way. Would be 2/3, right? Or 0.67. What would the angle be? What would be the angle of this Z2 over Z1?
-15.
Yeah, it'd be 30 minus 45 degrees. So it would be -15 degrees, like that. Okay. What if I wanted to multiply? What if I wanted to multiply? Well, in that case, I would say Z2 times Z1. It would be the magnitude of Z2 times the magnitude of Z1. And what do you think I would do with the angles?
Would you add them?
I would add the angles. Yep. So the angle of this guy would be, so angle of Z1 plus angle of Z2. So for the example I had there, Z2 and Z1, so Z2 is 2 angle 30, and this was 3 angle 45. What would be Z1 times Z2? What would that be?
6.
Yep, 6 with what angle?
80, 75.
75 degrees. Okay. So this is pretty straightforward stuff. In a lot of ways, you guys have probably seen a lot of this vector manipulation stuff before, right? One thing we should probably say, somebody talked about putting stuff into its components, right? So 3 angle 45 degrees. Here, let's say this is Z1. This is 45 degrees, and this length here is 3. How can I figure out the real and imaginary part of that thing? How can I use trig to help me with that if I wanted to figure out the real part and the imaginary part? What's the real part in terms of this picture? Where would I draw the real part?
Be on the x-axis.
Yeah, this would be the real part, and this height here would be the imaginary part, right? So how do I figure out the length of this side right here?
We use sine.
Yep, this is where I can use sine and cosine, right, to do my different things, right? So I can say that let me just, in general, I'll just call this the angle here, phi, right? I can say the cosine of phi is equal to what over what in terms of a triangle?
The base over the hypotenuse.
Yeah, so the base over the hypotenuse. In this case, it's the real part of Z over the magnitude of Z. And sine of phi, how do I define that?
Imaginary part over the magnitude.
Yeah, so the opposite over the hypotenuse, right? So the opposite is the imaginary part. over the magnitude, the hypotenuse, like that. Okay, so there's a cheat sheet that I'll post. All right, the problem 6 in the homework is really about just doing some basic manipulations of Z, or problem 6 is Z1 plus Z2, Z1 times Z2. So it's getting you to do some basic stuff. We're going to do some more advanced stuff with this for sure, but today I just want to kind of introduce the concept and talk about some of the basic stuff. This is no different than vectors and what you've done with vectors. It's just, you know, doing it and calling them complex numbers.
Ask a quick question.
Yeah, I'm gonna stop this here real quick and